Our first speaker is Tim van der Zee, 5-minute talk, energy dissipation by soft tissues during walking.
Thank you. So the mechanical work, is the audio okay? It's better? Okay. The mechanical work done during human movement is important for performance and largely determines the metabolic cost. Humans can do mechanical work with muscles, tendons, and soft tissues. Soft tissues do largely negative mechanical work and dissipate energy. Tissues can contribute to about 31% of negative mechanical work per stride during walking. But despite this large contribution, are mostly ignored during biomechanical analyses. Soft tissues dissipate energy that increases with walking speed and is larger in obese individuals. It's currently unknown which other walking conditions can influence soft tissue dissipation. And there are certain problems, namely that soft tissue dissipation cannot be captured with standard inverse dynamics, and current soft tissue estimates are complicated. I tried to extend the knowledge on soft tissue dissipation by trying to see if there's an effect of different walking conditions. Specifically, I manipulated walking speed, step length, and step frequency, quantified soft tissue dissipation, tried to see if there's a relationship with collision work. And I tried to solve the problems by trying to find a simpler measure for soft tissue dissipation. And specifically, I've looked at net sum joint work and peak ground reaction force. So using the center of mass approach, you can compute the center of mass power as the product of ground reaction force and center of mass velocity. Here we see an example. And this is a measure of the work done by the body. Alternatively, you can use inverse dynamics and compute the joint powers. And in this case, they are summed. The ankle, knee, and hip are summed. The result is pretty similar to the center of mass power, but not completely the same. The difference between the two powers is used as a measure for soft tissue dissipation, which is the shaded area. The reason for this is that the inverse dynamics includes a rigid body assumption, and therefore doesn't capture the soft tissue dissipation, whereas the center of mass approach can capture this soft tissue dissipation. So the shaded area here is soft tissue dissipation. Please note that the last part is not actually soft tissue dissipation, but more like swing work, and is more of an artifact of the method used here. And as done in Fu et al., you can use the peripheral center of mass work to quantify this. You can also specifically look at the collisional phase of tissue dissipation, as shown here. And I hypothesized that soft tissue dissipation increases with collision work, and collision work is the center of mass power integrated over time during the collision phase, as shown here. And this collision work has been predicted to increase with step length, and that's because step length, here we see an simple inverted pendulum model. Step length changes the angle between the legs to alpha, and this changes the direction and size of the ground reaction impulse, and thereby the negative work done on the center of mass. Specifically, it's predicted that collision work increases with step length squared when walking speed is constant, with speed to the 4th power when step frequency is constant, and with speed squared when step length is constant. Here's data on 7 participants walking on a treadmill in either constant speed, constant frequency, or constant step length. Center of mass collision work on the vertical axis. It's increasing with step length and speed in the first 2 conditions. There's not really an increase in the 3rd condition, which is a little bit surprising. Results roughly match the prediction. If you assume that soft tissue dissipation is proportional to center of mass collision work, then you can try the same predictions on soft tissue dissipation. Here we see that soft tissue dissipation increases with step length and speed in all the conditions, and roughly matches the predictions. This is also true for the collisional soft tissue dissipation. Here the standard deviations are a little bit smaller, and the effect with the constant step length is again a little bit strange. Collisional soft tissue dissipation relates to the collisional work, showing that there's more soft tissue dissipation when the collision work is larger. This is also true for the total soft tissue dissipation, but here the relationship is again somewhat more noisy. The relationship of net joint work is almost identical, and if you plot them against each other, you see that they are almost the same. And this indicates that net sum joint work is a good proxy for soft tissue dissipation, which has the advantage that it can be measured with inverse dynamics. Alternatively, you can use peak ground reaction force that also has a relationship with soft tissue dissipation, in that with larger peak ground reaction force you have more soft tissue dissipation, but this relationship is again more noisy. Altogether, soft tissue dissipation is proportional to collision work and increases with step length and speed according to a simple walking model. Net sum joint work seems a good proxy for soft tissue dissipation, and ground reaction force seems a reasonable proxy might be really easy to determine. Thanks for the funding. Thank you for your attention.
Your soft tissue work arises because of a discrepancy between measured kinematic data and measured kinetic data, right? And people might argue that there are several contributors to this discrepancy, one of them being soft tissue work. What are the other contributors to this discrepancy, and what are the relative contributions, or can you say anything about that?
So you say that it arises from a discrepancy between kinetic and kinematic. Can you maybe elaborate on that a little bit?
Okay, so I put a person on a force plate and I measure kinematics. And from these kinematics, I can calculate the motion of the center of mass. And then I also measure force, and from the force I can also calculate the motion of the center of mass. And these two motions do not agree with each other, and this gives rise to what people call residual forces and stuff like that. And there might be many contributors, or several contributors to these discrepancies, like measurement error, or name it. So I wonder, what is the relative contribution of other sources, or do you have any inclination on that?
Yeah, that's a good question. So you of course have measurement error, but I don't see a reason why that should have an effect with walking speed or step length as predicted in the ways we have predicted. I'd rather, my assumption would be that it would be a kind of a random effect, which would not relate to speed or step length. But could not explain the results here. Right.
So it might be that that an artifact is covariant with peak ground reaction force or something like that. I don't know.
Andy?
I have a question and maybe a suggestion, which is, or criticism and maybe a suggestion, which is that it seems like you assume that you have rigid objects and perfect hinges and massless actuators, and you find there's a discrepancy, and you know there should be a discrepancy because of soft tissue deformation and maybe elastic internal components, for example. And then you say, my calculation doesn't come out right, and then you assume the amount that it's not right within that calculation is because of the things that were not in the calculation. And it doesn't feel mathematically or logically correct. And then if you wanted to say check whether it's logically correct or find out what the degree of approximation is, it seems like you could put on your computer a model of a person, put in that model a little spring and damper attached to every joint that has 2 degrees of freedom or 3 degrees of freedom, and then just go through your exercise and find out, is your error the same as the soft tissue deformation in that model? I mean, I don't think, maybe it will come out about the same size, but I don't see why you know that ahead of time, or maybe you do.
I think that's a good thing to do in future research. I think this research is a good first step to show that there are some soft tissue dissipation and how it relates to certain variables like speed and step length, and follow-up might be modeling it.
Yeah, so similar space of question. I'm wondering if you just had them carry a jug of water, or like some sort of a jacket full of some sort of wiggly gel, where you could actually manipulate the soft tissue dissipation, and then see if you can sort of make predictions on your model based off of that.
Yeah, that would indeed be a good future experiment. Yeah.
Okay, thank you, Tim.